Welcome back, everyone. In our lecture series based on broadening of spectral lines, we have already discussed natural broadening, the mechanism, what's the reason behind natural broadening, and we also did the derivation. Today, we are going to discuss collision broadening, which is also an example of homogeneous broadening. That means all the atoms will behave in similar manner. Now, you can see here in the picture depicting a box, there are various atoms which are just moving randomly. This is true for gas, this is true for liquid as well. But in solid, we say that solids have got definite shape and definite volume. But that doesn't mean that atoms in solid are stationary. Always remember that atoms are never stationary. They would be stationary only at absolute zero. That 0 Kelvin, the temperature that we study, at which all the processes, all the biological processes, all the molecular motions, they just stop. That is the temperature whom we call absolute zero, the 0 Kelvin. And we have not achieved that temperature yet. That is minus 273 degrees Celsius, too low a temperature. So in routine, what we find is that atoms are not stationary. Even if in solid, atoms are arranged in a definite pattern, they are kind of fixed, but still they keep on oscillating about their mean position. They just keep on vibrating, you can say, about their mean position. So they are never at rest. So if we consider a system, particularly a gaseous system, suppose we are using a gas laser, then definitely the atoms would be moving randomly. Now this word, the collision broadening, that simply suggests that the broadening in the spectral line would be due to collision. And that collision would be the collision between randomly moving atoms. One more thing that I want to state here is that some textbooks say that when atom makes transition from one energy level to another energy level, photons are emitted. And sometimes few textbooks also mention that when electron makes a transition from one level to another, then there is the emission of some radiation which further leads to finite width of spectral line. So some books do use the word atoms and some use electrons. So always remember that really doesn't make any difference, because we know that atoms, they include nucleus, positively charged nucleus, and then we have electrons which are revolving around nucleus. And we have also studied the Bohr's model of atom, which says that electrons revolve in certain specific orbits, they don't radiate energy, and it also states that electron can only exist in those states where the angular momentum is an integral multiple of h cut. Further, the third postulate of Bohr says that whenever electron makes transition from higher energy level to lower energy level, photon is emitted, because it doesn't need that much energy. And if an electron is revolving in lower energy level, then if a photon hits an electron, it would absorb that energy and then it would jump to some higher level. Basically, it's the electron which is doing the whole task, but we usually say that atoms are jumping. Why? Because whenever electrons, they make transition from lower energy level to excited upper energy level, we say that atom gets excited. Usually in nuclear reactions, we write that whenever there is any nucleus, we denote it by star if it is in excited state, and then we say that it just gives off some energy gamma and then return to normal state or ground state. So when the atoms are in ground state, that means the electrons are not making transition to higher energy levels that much. And the moment electrons are jumping to higher energy level, we say that atom has reached the excited state. So there is excited state and there is ground state. So you can use either alternative, you can use either word. You can mention that electrons are making transition, but it is better that we stick ourselves to atoms. So I will be using atoms whenever I would say that there is a transition between two energy level. I would say the atom transits from one energy level to another, and then photon is emitted or absorbed according to the case. So these are the points that you have to just remember. Let's consider that we have a gaseous system. In that case, we are saying that gas molecules, they are in state of random motion. They are just moving randomly. But now we can play with this randomness. We can change the behavior of these randomly moving atoms or molecules. How? Suppose we apply high pressure, then what would happen? When we apply high pressure to the system, that means suppose we are having a piston and we are just compressing the system by applying pressure. Now, the atoms are not going anywhere because it is a closed box, you can see. And all the molecules, all the atoms, they are just moving randomly and there is no escape for the atoms to go. So they are there, they will stay in the box itself. But if you compress the box, if you increase the pressure, the available space, the amount of space available for the atoms would decrease and they would come even closer. What I mean to say here is that if we have a box where we have total of 10 atoms, so obviously they would be moving randomly, hitting the walls of the container and might also be hitting each other because if they come in the path of each other, they would definitely collide. But what if we increase the pressure? If we apply pressure via piston, it would compress the box. Now, volume of the box has decreased. You can see this was the original volume, original size of the box, but now it is only half. But the atoms have not gone anywhere. They are still inside the box. So again, we have the 10 atoms here, but now they are much closer and they are moving. So now the probability of collision between the atoms would definitely increase because now they would hit each other. They would come in each other's track and they would hit each other more. So there will be more collisions than this case. Here, lesser collisions, and in the second case, there will be more collisions. So if this thing happens, if a gas is at high pressure, we can expect more collisions and those collisions would result in collision broadening. How would that result in? We will study a bit later. So the concept I'm talking about is that one thing we can do is providing high pressure. But high pressure can result in more collision. Similarly, second aspect can be high temperature. What if we raise the temperature of the system? In that case, what would happen? We know that if we increase the temperature of any system, the molecules start vibrating faster. That is, the kinetic energy of molecules or atoms increase. So they would start moving rapidly. And even then, the possibility of collision would increase. See, if you are driving, we always say that we should not drive at faster speeds because if we are driving fast, the possibility of us hitting something increases because it's very difficult to control the speed and then we can just hit anything, whatever comes in our way. Similarly, same is the case for atoms which are moving really fast. So if they are moving really fast, within fraction of seconds, they are just going here and there. So the possibility of colliding with each other would increase. So that means there are two possibilities by which we can increase the collisions between the atoms. One is high pressure, another one is high temperature. In case of high pressure, what we are doing is we are limiting the space available to the atoms, and that's why they have no more space to go, and they would come in each other's track and they would hit each other. So the pro- probability of collision would increase. Another thing is high temperature. At high temperature, basically we are increasing the kinetic energy of atoms, and they would start vibrating or moving rapidly at higher speeds, and again the possibility of collision would increase. If we have a box like this and there are gas molecules which are in constant random motion, this motion increases much at higher temperatures, and as a result of which the atoms they they collide with each other more frequently. They will just keep on colliding with each other. Process of collision would increase. Now, how is this related with the collision broadening that we are talking of? Remember, we are talking of the system where we have atoms which gain energy and they reach the upper energy levels, and sometimes they just lose energy and return back to lower energy levels. And this photon is captured in the spectrum. Now we know that in all these transitions, natural broadening will always be there because it is the inherent nature of the system. This is due to the finite lifetime of the excited state. Due to this and due to the Heisenberg's uncertainty principle, we know that we cannot tell the energy of any excited state with complete surety. There is uncertainty because the lifetime of the excited state is quite less. It could be of the order of 10 raised by minus 8 second or even lesser. It means this state would exist for quite a short time, and we will not be able to detect it. The moment we would try to measure it, measure the energy of that state, it would be just gone. This happens so quickly. The lifetimes are really short. And that's why even if we try, if just by using some instruments, we try to measure the energy associated with that particular excited state, it is not possible because the lifetime, they are finite, and here in the case of atoms, quite less. So we have the uncertainty in the lifetime of the excited states, and that is also not fixed that a particular excited state would have a fixed lifetime. It has finite lifetime. It means it's never gonna exist for longer times or for infinity, but the lifetime whatever it has, that is an approximate one. That means a particular excited state may get vanished or may disappear after 10 to the power minus 8 second, or sometime 10 to the power minus 7 second would be the time, sometime 10 to the power minus 9 second would be the time, and so on. We cannot be sure. So if we are not sure about the time, we cannot be sure about the energy. And that's the reason that even the the levels, even the two levels that we are talking of between which the transition is taking place, its energy can be uncertain, which leads to photon of some other frequencies as well. So this is the thing which would always be there. Whenever we obtain a line spectrum or the spectra, that would be having natural broadening, because this is by default feature. It will always be there. Now, what happens if there are many atoms present? Then they would start interacting with each other as well, because then they won't sit idle. The situation is if there are quite less amount of atoms present, very fewer atoms are present, in that case we don't expect collision to happen. In that case, all we can expect is the natural broadening. But what if there are many atoms present, and what if we increase the pressure? In that case also, all the atoms, they would come closer to each other, because now they would be hitting each other. And what if we increase the temperature? Even in that case also, the random motion would increase and they would start hitting each other. So this is the situation. If these two situations arise, then there is possibility that the atoms, they would start colliding with each other as well. Now comes the main point, that if while transition, while the atom is making a transition from one energy level to another energy level, another atom comes and hits it, then it would definitely affect the photon that is being emitted. So if this atom is trying to come down while emitting a radiation, and this atom comes and hits this atom, collides with this atom on its way back to lower energy level, then the radiation that is being emitted, that would also be affected, because now it is not due to just one atom. In fact, there is some effect due to the other atom as well, because other atom also hit that atom and it must have given some amount of energy to it while hitting. Whenever these atoms or these tiny particles, they collide with each other, they transfer some amount of energy to each other. Some sort of energy transfer is always there. And that happens that sometimes one atom, after collision, they just change their directions. As here you can see that two atoms, they are just colliding with each other. This is the before collision. They just came, hit each other, and then they just went off in different directions. And during that collision also, the photon got emitted. So this emitted photon would be having slightly different feature than it would have if there was no collision. If the atom was just coming on its own back to lower energy level, then the photon emitted would have been different. But now the photon that is being emitted would be different, because it has effect of this atom as well. This atom must have transferred some of the energy to this atom, and so on. The final photon which is coming out, that is a different one. So this is collision broadening, because now there is no natural broadening. Now what happens, that we get a peak, which is the central frequency peak. Then we are getting a Lorentzian distribution. So now the central frequency is there. Then the natural broadening would also give us few frequencies. And now the collision broadening would also give us frequencies, because now this emitted photon would be different than the photon emitted during natural broadening, because here I can write that this is the natural broadening and another one is collision broadening. Here atom is just coming back on its own, so the photon that is being emitted is slightly different. The spectrum will be having natural broadening only. But in case of collision, there would be some atoms which are coming on their own. So we would be having same photon, because ultimately here atoms, they behave in similar manner. So we will be having that sort of photon also. But if we have the atoms which are colliding with each other, if there is a collision between two atoms, when atom is making transition to lower energy state, and it can happen in between also. Suppose atom is coming here and another atom comes and just hits it. Now in this case, the photon that is being emitted would be different than this one. This is due to normal transition of atom between two levels, which is the natural broadening, just like this. But here this photon is different, because while atom was making transition between the two levels, it got hit by some other atom. So that atom must have transferred some energy to that atom, and that's why the energy of photon will also be different. So here spectrum would be having natural also. Natural broadening is always there, plus there will be collision broadening as well. Natural broadening is the inherent feature, so it will always be present. But all we have to do is check whether some other collisional, some other broadening mechanism is there or not. So if your gas is at high pressure or temperature, then definitely we would be expecting collision broadening as well. Now the word I'm going to use now is perturbation. I have to use a word perturbation. What is this? This word I'm going to use. So perturbation means a deviation of a system, moving object or process from its regular or normal path or state caused by an outside influence. So what is happening? We have an atom. This was its normal routine. That atom was, after some time, when once the lifetime of the excited state is over, it jumped back to lower energy level and was emitting a photon. This was the normal behavior. But now what happened? Some other atom came and hit that atom, and it just disturbed the atom, which obviously changed the overall behavior of the system, and the photon that was emitted was also a bit different than it would have been when there was no collision. So whenever there is a deviation of a system, moving object as atom we can say, or process from its regular or normal state or path caused by an outside influence. Here it's not an outside influence, in fact here there is another atom which is doing the thing. So basically we are just disturbing the atom. So once you disturb something, disturb the atom from its normal behavior, then you say that your system is perturbed, or we say that there is perturbation. So this word I'm going to use. So now just understand what does this mean. The finite deviation of a radiation process when atom makes a transition from one level to another, that leads to finite width of line. We all know that, which is due to Heisenberg's uncertainty principle. But now when we have a gas with high pressure or a high density gas, we can also say high density. High density means there are many molecules in small system. Many atoms are there in a very small region. So we say high dense region. So high density gas can also be there, or high pressure gas can also be there. So in that case, more atoms will be present. Like here, more atoms would be present, and the radiating time can be greater than the interval between atomic collisions. So now I say that radiating times can be greater than the interval between atomic collision. It means the lifetime of excited state can be longer than the time interval between two collisions. So if more atoms are staying here, suppose the lifetime of excited state is bit longer than the time interval between the collision, so more collision would be happening, more atoms would be colliding this atom before this lifetime of this state is over, and that would result in some sort of perturbation. And this perturbation by colliding atoms causes the premature transition and emission of photon. Very important. For a high pressure or high density gas, radiating times can be greater. Now what do you mean by radiating times? That the time interval between which the transition would take place. Radiating time, the time interval between which the radiation would emit. So that can be greater than the interval between atomic collision, because if the lifetime of excited state is longer, then atom would stay there for some time. What if another atom comes in between at that time? In meanwhile, what if another atom comes and the atom is still sitting there and it would just hit it? So this radiating time, they can be greater than the interval between atomic collisions. before the lifetime of excited state is over and another atom comes and hits the atom, then what would happen? This perturbation, because it would disturb the atom definitely by colliding with it, it would disturb the normal state of the atom. So this perturbation by colliding atoms causes the, this is very important, this is the main reason why do we get collision broadening, or what actually happens there, how is collision broadening different from the natural broadening. This is the thing, that this collision of atom by another atom before the lifetime of excited state is over. This is very important, that before this is happening, before the lifetime of excited state is over. So if this happens, then another atom would come and just hit it, and that hitting would result in premature transition and emission of photon. So suppose atom was sitting here on its own and it was just waiting for the lifetime of this excited state to get over. It was just doing good. And then, because there was some time, what happened? In the meantime, another atom came and it just hit the atom. Now, see, if you are sitting somewhere, if you are standing at some porch, at some level, you can consider this to be stairs. If you are standing on stair, if you are at upper step in a staircase or just ordinary stairs, and if someone comes and just pushes you, hits you, then there are chances that you would jump, you might fall also, or you might jump to lower step. This is a normal situation that we can experience and we can imagine. If we are standing on stairs at some higher step, and if someone comes and just pushes us or collide with us or hits us, then we might fall, or we might just jump down to some lower step of the staircase. Same thing is happening with this poor atom. This was just sitting here, it was just waiting for the lifetime of excited state to get over, but in the meantime, another atom came, because we are saying that the radiating time can be greater than the time interval between atomic collision. So collision is happening. It collided with it, and in collision, definitely most of the time atoms exchange energy. So it just pushed it and caused premature transition. So when premature transition occurred, atom jumped back to lower level. It had to, because it had no other option. This atom just pushed this atom, and then it fell back to the lower level. And whenever atom jump from some higher level to some lower energy level, photon is always emitted. But now this emitted photon is different in behavior or different in characteristic than the photon that would have been emitted if atom would have come on its own. If this atom would not have come, this red atom wouldn't have hit the atom. So always remember the main reason. If before the radiating time or before the lifetime of excited state is over, in that time another atom comes and hit the atom, it would cause premature transition. It would just push that atom, and that atom would fall back to lower energy level. And whenever atom jumps from one level to another, photon is always emitted. But now this photon would be having slightly different behavior, slightly different characteristic, because this atom might have transferred some energy to this atom. So as a result, energy of this photon would also be different. So the decreased lifetime of state, because now this has been done. There was a finite lifetime of the state, but since this atom, this red atom, it just came and hit this green atom, so this atom had to fall back to lower level. And once this happens, this state is gone. If no atom is sitting, if no atom is present, that energy level no longer exists. The moment atom is gone from energy level, that energy level or that energy state itself disappears. So here this atom, this red atom, make this green atom jump to E1, and that's why E2 is gone. It vanishes. So that means we have decreased the lifetime of the state because it had ended, it had disappeared earlier than its original lifetime. And this creates an increased uncertainty in photon energy, and the photon that will be emitted will be having slightly different energy, which would result in broadening of the spectral line. So this is the main reason of the broadening. This paragraph is very important. You have to remember this as it is. This whole statement has the complete essence of this mechanism. It has the complete meaning and the reasoning. Why does collision broadening occur? So whenever perturbation is there by colliding atoms in high pressure or high density gas, it results in broadening of emission line, or it could be absorption line, and so on. And the same we experience in sodium lines. We experience this broadening in sodium lines, which are usually D1, D2 lines at 589 nanometer and at 589.6 nanospectrum. So this broadening in frequency width, because we know that there is the line spread delta omega naught. So there is an increase in the width of frequency. So that broadening in frequency width is dependent upon the separation of the perturbing particles. So here these perturbing particles means the atoms which are colliding. So it depends on the distance or the separation of perturbing particle, the distance between the colliding atoms. That is, we can write delta nu, the central frequency, the change. Delta represents the change or the spread. So spread in frequency width is proportional to Rn, where R is the separation between perturbing particles. Further, we have this value n. This n states what kind of atoms are colliding. This n tells the nature of atoms. If n is 2, this implies that we have either ionized atoms or electrons colliding. So either some free electrons are coming or some ionized atoms. So ionized atom means that either they are having positive or negative charge. So n equal to 2 implies that some ionized atoms or some charged particles are colliding with the atom which is present on the upper excited level. And if n is 3, then that implies that neutral atoms are bombarding the atom which is sitting over the upper excited level. This is important. And the word, the separation of perturbing particles, or we say that the distance between the two colliding atoms. One more thing that we should understand here is that when we say that atoms collide or there is collision between atoms or one atom hits the other one, we are using this terminology. There is no actual collision. Atoms don't actually hit because they cannot. You know that atoms contain positively charged nucleus and then there is just negatively charged electrons. All atoms are same, right? So if one atom is there and another atom is approaching towards it, that would also be having positively charged nucleus and a cloud of negatively charged electrons. Now these electrons, they both are negatively charged because electrons are always negatively charged. And we know like charges repel. When like charges repel, so these electrons would repel each other. So these two atoms, they can't come closer enough. They would come closer up to a certain limit and then they have to turn back because after all, it's the electrons which are facing each other and they would repel each other. So the minimum distance that these atoms can come to, the minimum distance between these two atoms is known as distance of closest approach. The atoms cannot come closer more than this x. They cannot come closer than x. X is the minimum distance between them, or we can say distance of closest. So this is the distance of closest approach, and the atoms cannot be brought further closer than this distance. So then they would go in some other direction. We can see that these atoms are coming here. Just for pictorial representation, we do show that atoms are actually touching each other, they are hitting each other, but in reality this doesn't happen. They just come close up to a certain limit, which is distance of closest approach, and then they just change their paths and go some other direction. There is a distance. Suppose this is our atom and this is another atom on the sitting on the excited energy level. So now this atom can approach this another atom. This would never directly or would actually physically hit the atom. It can just come closer and closer, and because we know the electrons would start interacting with each other and they are like charges, so they will repel. So this could be the distance, or atom can travel any distance, but it is just that it would pass through it very closely. And when atom passes through another atom at such shorter distances, it does affect the atom. It's not that only when they actually hit each other that it would actually affect that atom. No. In reality, atoms never collide, never hit each other physically. They just pass through each other. They can come closer only until the distance of closest approach. They cannot come closer than that. See here, this atom can come closer only at this point, and then it has to go somewhere else. But still, it has the power to affect this atom. Their fields, their electric fields would affect each other, and the photon that will be emitted by this atom now when it jumps back to lower level would be different. So keep this thing in mind. The concept of collision. What does collision actually mean here? And after collision, as we are saying, they just go in different directions. Now we know that pressure and temperature of a gas, they can result in collision. As temperature of gas increases, the collision interval and the broadening becomes more pronounced. And atoms in such a gas cannot be considered as isolated atoms. Whenever we have high pressure or high temperature, then atoms cannot be considered as isolated. This thing is very important. Whatever I'm writing in paragraphs, the statements I'm writing down, they are really important. You have to remember these statements as such, and whenever needed, you can use these statements for answering the question, because these statements contain the actual reasoning and the actual phenomena which is occurring. So whenever we have a gas which is at high pressure, we have high density gas, or if the temperature of the gas increases, in that case atoms cannot be considered as isolated systems. Isolated means single atom. Why? Because atoms would be closer to each other now. They would be affecting each other, they would be hitting each other. So isolated system can no longer be there. And those systems need to be treated statistically such that due to perturbations caused by the presence of surrounding atoms, there is no longer a fixed separation between any two energy levels. Again, the problem is the same, that due to this perturbation, now we know that when an atom is sitting, and other atom just comes and collides with it, it causes premature transition, and this E2 is gone, this vanishes, and this atom drops down to lower level. There is no longer a fixed separation between any two energy level, between these two energy levels now, because this has gone, this has disappeared, and we can't actually tell what is the exact distance or the gap between these two levels. This the thing that we always use, that whatever is the amount of photon emitted, that the energy is equal to the difference between the energy of these two levels, the very important concept, the statement that we always use, basically it's no longer that important, or we say that that thing doesn't actually happen. You saw in natural broadening also what happens, that again we cannot tell about the energies. There we cannot tell about the energies of the states due to Heisenberg uncertainty principle. Here, due to collision, what is happening, that there is premature transition and this excited state is disappearing before its original lifetime. Once the atom has gone, this state would disappear. So we are decreasing the lifetime of the state here, which again tells us that we don't know what is the exact value of energy of these two levels. And again, the photon that will be emitted, that will be different one. So whenever we have a process of absorption or emission, the energy of absorption line will be uncertain with a width that is dependent on the pressure or temperature. So that width now in the line, that line spread would be depending on these two things, whatever the situation is. As this is homogeneous broadening mechanism, collision mechanism, the line profile, the spectral line profile that we will obtain would be a Lorentzian one and not Gaussian. We did the differences between homogeneous and inhomogeneous broadening mechanism, and this was the point, that homogeneous mechanisms we usually get Lorentzian distribution, and in inhomogeneous mechanism we usually obtain Gaussian distribution. So here we are going to get Lorentzian distribution, which would be, and the characteristics are basically narrow spike with longer wings or tails, you can say. Let's do an example. Let's try to understand this collision broadening with the help of an example. Here you can see a lamp. We have used a sodium lamp. I know, I really apologize that the videos are getting really long, but these concepts are really important and I really feel like I should give good explanation of each and every aspect of it, and also the derivations are really long and it's very difficult to cut short or make different sections of a particular video or a topic, because this topic is all in all a single topic. Here I'm just discussing the introduction part, the why part of collision broadening. I have discussed what is collision broadening, why does this happen, and now we are going to discuss the exact example by using sodium lamp. So this is the sodium lamp and this is how it looks when it glows, a glowing one. This would definitely help us to understand what happens to the spectrum with time and where do we actually start seeing the collision broadening. Here what you are seeing is the spectrum of sodium lamp. We have just switched it on. So this is the cold lamp spectrum, and you can see these two doublets often denoted by D1 and D2. A cold lamp means the lamp is not that hot. Definitely when the lamp is off, it's not glowing, it will never show any spectrum. But the thing is, we have just switched it on and that's why it's still cold. It's not heated up at all. So cold lamp spectrum, we know the temperature is not that much high. And again here, the situation is that it's low pressure system we are showing. And we are simply getting these two lines. These two doublets are there and you see it's almost like a spike. We are not seeing anything like a curve or a spread is not there. In fact, what we are seeing is just a spike, a narrow but straight spikes, and even the spread is not that much. You can see these are the two lines and the spread is just negligible. And you see this spread, whatever the least amount of this negligible spread that you are seeing, that is due to what? Now you should know that this is due to natural broadening, which is the inherent feature of excited state, and Heisenberg uncertainty principle gives us the reason. So this minute, this negligible spread that we are seeing, that is due to natural broadening, but still it is not that dominating one. We can observe it and we can clearly see that, okay, there is just natural broadening, nothing else. The pressure is low, temperature is low, so everything is fine, and the spread is not that much. Now let's see what happens after some time. Look, after some time, when lamp actually starts heating, this is the spectrum that we obtain, and see how different it looks from this original spectrum that we obtained right at the beginning. This is the beginning stage when our lamp was cold. This is cold lamp spectrum, and now this is spectrum when lamp is heating. Now you see here we had just two lines and the spread was also negligible and they were just showing as spikes. And now the two lines, they have starting getting wider. You can see this, we are getting narrow spike. Narrow spike is there, yes, narrow spike is there, but this, it is started getting wider. This is widening, and that too around the tails you can see widening. And this is typical Lorentzian distribution. Again, when temperature further increases, see if this is at temperature T1, this is at temperature T2, this is at temperature T3, because lamp is slowly heating, and we have our T3 is greater than T2, which is greater than T1. Now see, now you can see even wider spread. First it was less and now it has gone wider, and here you can see, oh god, this is really wide spectrum you can see, and we are getting narrow spikes. This narrowness is there, but see how long the tails are. The tails are getting longer. Here also you can see the tails are getting longer, so extended tails and narrow spikes, which is a typical Lorentzian distribution. And you can very well identify now that how much different this spectrum looks from the one which was at the beginning. Though it is of the same element, we are using same sodium lamp. We have not changed the lamp. It's just that with time the lamp is getting heated up. In the beginning it was cold, so we were just getting pretty good two lines with not much spread, and whatever little spread was there, that was due to natural broadening, which is the inherent natural trait. But as the temperature started increasing, you can see for the same lamp, for the same sodium lamp, the curve, the peaks, they are getting wider at the center. They are still narrow peaks are there, narrow spikes are there. This is a particular, one curve is more like this, and other curve is more like this. So this one is Lorentzian and you can relate, whereas this one sometimes tells to be Gaussian. Here we are getting Lorentzian. You can see the narrow spikes, narrowness is there, but the tails, or sometimes we call them wings, they are getting wider. So they are getting wider, and what we are obtaining is simply the Lorentzian distribution. As temperature is increasing, we are getting the same plot as getting wider. It's getting bigger, wider at the tails. This is the final spectrum that we obtain. Now you can see all ranges of frequencies there. Now you know, originally it just had these two frequency lines. And we know that sodium lamp, it gives out yellow colored lines. Yellow spectrum is there. So we can see here the yellow portion and two lines clearly. Same sodium lamp, but as temperature went on increasing, the graph, the plot, it started spreading at the center, and then more and more colored lines started emerging. And here, see, you are getting red as well, you are getting orange, you are getting green and blue portion as well. Imagine for sodium lamp. And here the final, because lamp has been running for quite a long time now, and we can see all sort of frequencies now. So we have here range of frequencies. This is how collision broadening happens. This one, what we are getting, this minute spread is due to natural broadening. Now you can see it yourself. What's the effect of natural broadening, and then see what is the effect of collision broadening. Collision broadening, why? Because as temperature is increasing, the atoms, the randomly moving atoms, they start colliding, they start hitting each other, and therefore they affect the emission of photons. They result in premature transition of atom and thus affect the resulting photons. And here we are getting all sort of frequencies, all colors you can see here, and that is all because of collision broadening. This is all about this was an introductory, though quite a big video, but it was introductory part. What is it all about? And we also discussed the reason happening and also understood it with the help of an example from the spectrum obtained with the help of sodium lamp. And now in the next lecture, we'll do the derivation of collision broadening the same way we did for natural broadening, and we'll continue. Thank you all for joining me today.